The last class we were discussing briefly hydroformylation reactions, and as you have seen, it requires three different gases, olefin, hydrogen and CO, to give you either linear product or branch product. Now these are truly important intermediate, and the reaction mechanism, as we understood, will be the formation of this hydrido-cobalt complex, hydrido-CO3, and then olefin coordination, and then this hydride will be transferring at a beta migratory insertion mode to give you these either this branched intermediate or linear intermediate. Hello. Okay, overall then we'll have an opportunity to work a linear product where carbonyl insertion will come into picture. The carbonyl insertion in coming into picture and inserting, so linear alkyl carbonyl intermediate is happening, and then oxidative addition into hydrogen to give cobalt dihydrido complex, and then reductive elimination to give you the linear product formation. Right, that's what the mechanism. But as you have realized, there is a product formation, similar product formation, which will be branched in nature in these cases, which will have exactly similar catalytic cycle. We can draw another catalytic cycle over here, right? Well, but the problem is, of course, industrially or even in laboratory, synthetic laboratory, we don't want two products. We want one product. How to get one product? This is one of the issues. The issues definitely is deeply rooted. You can try to solve this problem with this, but you can change the solvent, temperature, different other parameters as you much, and the pressure. It would have some effect, but not really a great lot of effect. So therefore, the best way to solve this problem is to use a phosphine ligand. So one of the carbonyl of this 4 carbonyl, you displace it with a phosphine ligand. That ligand, electronic and the steric properties of this R group will control the hydroformylation reaction, or the linear is to branched ratio, which in the previous cases we were getting, let's say, maximum 4:1, that perhaps can be controlled. These are very, very important issues to solve. For example, with cobalt, we have been seeing this sort of complex, the reactive intermediate. You have 4 carbonyl species, making these carbonyl species not that very stable. That is because, of course, if you have a high pressure of carbonyl, this will be stabilized to some extent. And if you do not have high pressure, the stability of this complex will be taking a hit, right? It's not going to be stable. And also, if you have, so that means low pressure of CO is not good for this complex. And also high temperature is also going to create problem. Low pressure as well as high temperature is going to create problem for this sort of reaction, but this is unavoidable for this reaction to have the pressure fluctuation as well as temperature, right? Usually you see you can have 180 degrees C also. Overall, this is not really that much of a reliable catalyst, although the reaction can be done, but mainly we are talking about linear is to branch selectivity is also a problem in here. Okay, this decomposes at high temperature and low CO pressure. Now, if you now displace this one of the CO, if you displace this one of the CO with this PR3 group, if you displace one of the CO with the PR3 group, then what happens? This gives better electron, and then the stability of the whole complexes goes up. More importantly, the hydridic character, this becomes more of a nucleophile, and the hydridic character increases. That leads to the increase in reactivity. Right, increase in reactivity that can be in turn calculated into the fact that you will have a better selectivity linear is to branch from 4:1, and that is what we are trying to discuss over here. The electronic effect on phosphine can be modulated, can be changed. You can have different R group, for example methyl, ethyl, isopropyl, propyl, butyl, and the bulky phosphine ligands you can use. There are many phosphine ligands, one can vary pretty easily for this sort of complex. Although by doing so you may decrease the reactivity a bit due to the steric effect and overall, but nonetheless you have a better hydrogenation capability. The stability of the complexes increases. Steric bulk of PR3 influence the insertion direction of alkene to CO complex and geometry of intermediate. That means anti-Markovnikov addition will be really favorable. This is when, if you go back to again, so the main catalytic cycle, this is where the hydride is adding. This is the anti-Markovnikov addition. This is the primary alkyl species is forming. And this is the Markovnikov product where hydride attaches on the more hydrogen containing center, and it gives a secondary intermediate to leading to the branch product. Now, if you have, instead of 3 CO, if you have 2 CO and 1 PR3, this process, this linear product formation, this process becomes really feasible. This process becomes easier, and we will be then able to promote a much better selectivity issue. Sorry. So we'll have an opportunity to have this catalytic cycle much better if you have phosphine over here. One of the CO is replaced with phosphine, right? Of course, this has been done, and it has been an active areas of research, as you can understand, for this hydroformylation reaction. There are many synthetic reports, many research groups have been involved, even in many industry have been involved in developing these synthetic skills of these reactions. Overall, this is a schematic diagram which shows that why linear is to branch ratio becomes better. Previously, it was 4:1. Now it is becoming 9:1. 4:1 with this cobalt tetracarbonyl complex, hydrido tetracarbonyl complex, but with this BU3 complex, HCO2 BU3 complex, this becomes a HCO3, right? HCO4, and then with this one it becomes really better. Okay, better as compared to HCO4. Why is that? Because this hydride transfer you see is preferred over here. This is more hydridic, it attacks. Of course, this is the less bulky group. It is interacting with the metal center. This is the most favored. This is the more bulky group. R group is over here. Whether hydride is attaching over there where R group is there, or hydride is attaching over there where R group is not there, that's the question. Now, in this orientation, as you can see, the more sterically bulky group is not attached with the metal center. Less sterically bulky group is going to be attached with the metal center, in as you see in here. So this is going to be the preferred orientation if you are to get the linear product, and that's why the linear and branch product becomes easier. Previously, such if you are not having this butyl group, then you have a mixture of product formation, right? As you see, 4:1, 1 being the branch product. Of course, still the linear product is the major product if you have this HCOCO4, right? If you have HCOCO4, still the linear product is the main product, but branch product is forming considerable amount. You suppress the branch product formation by having this tributyl phosphine. Once again, I repeat, it's not that linear product was never really the problem in formation. Linear product was forming. So in this case, when you have all carbonyl, you have 4:1, linear is to branched, but this become 9:1 for PBU3 because you need just little bit help, and that help is coming in the form that this hydride remains more hydridic. So attaching at this center, it becomes not much of a problem, and the primary center is attaching with cobalt. That is where this reaction is being favored more than the branched intermediate, where branched intermediate would require the R group is associated with the cobalt, and cobalt has a bulky PbU3 that is somewhat disproved or not really possible in these cases. So the branch product formation is decreased due to this PbU3 presence. So this is not a preferred intermediate compared to this one. Of course, it was never a preferred intermediate. It was 4:1. Further, it improved to 9:1 when you have a phosphine ligand as this. If you don't have phosphine ligand, you have 4:1. If you have phosphine ligand, it becomes 9:1, because by making this one more preferred and by making this one less preferred, you do the reactions. Okay, I hope it makes sense. If you have any question, I can try to answer. Do you have any question? Any of you have question at this point? Okay, so we can move on, and this is where it is important to understand that these are simple principles which governs the product formation, and it dictates what way industry will use it, right? What type of product formation one would expect in industry, and what are the catalysts one would take. And overall, these underlying scientific principles are simple enough to make a decision and move forward. Often for a given olefin, you need to optimize the reaction condition before you go for large scale preparation, but the problems, knowing the problems and trying to address the problem beforehand will always give an advantage to the researchers involved in these processes. Okay, let's move on to another exciting domain, and that is the asymmetric hydroformylation reaction. Of course, for the linear cases, linear product formation, you do not have any asymmetric center, right? This is what I was telling earlier. If it is a linear product formation like this, there is no stereo center. In a way, this is a boring substrate, you know. Of course, if you need it, it's an interesting substrate. But if you don't need it, there is no stereo center even. So this hydroformylation reaction cannot be used for generating stereo center in this sort of compound. But the branch product, this is the linear product, right? But the branch product is always inherently exciting because you have a stereogenic center, or you have an opportunity to generate a stereo center, right? So this is where, as you see, the rhodium catalysts are taken, and 50 with a chiral ligand has to be chiral. 50 atmosphere of carbon monoxide and hydrogen gas is taken. Now you might be thinking, why all of a sudden it becomes branched is to linear 88:12, right? This is like 7:1 or 8:1, whatever it is, 7:1, 7.5:1. And why is that? Previously, so far, we have seen the linear product is always the major product, no matter what. Whether you take all the carbonyl or PR3 improves it, but linear remains the major product. Now, what made it the branch product becoming the main product? And then if we understand that, then we can try to see the stereo center generation. So what we are trying to say that it is not a simple olefin we are taking here. We are taking a styrene, so which has a phenyl ring. Now, having a long chain aliphatic alkene versus styrene is a completely different ballgame. In aliphatic substrate, you have a metal primary alkyl species formation after this beta migratory insertion. So you have linear versus branch product formation. Now, linear product is more stable because the steric hindrance that metal ligand will have from this methyl group, right? So this is due to the steric region. This is not really favored. What, of course, you know, still you can see 4:1 formation is going on, and so it's not impossible to form. Just it is not preferred. Okay. Okay, so the metal alkyl in primary, so primary metal aliphatic metal alkyls are more stable than the secondary, and that's why you see 4:1 formation, which is fantastic. Now what happens, the table is really turned around in these cases when you have a styrene, right? This phenyl ring is, of course, you can say that it is bulky. Why such a bulky group still favoring the secondary alkyl group? And that is simply because this is a negative charge. Negative charge is delocalized into the phenyl ring, and that stabilization gives the edge for the branch product formation. So both linear as well as the branched intermediate or the corresponding linear and branch intermediates are likely, but the stability of the aliphatic alkyl is primary greater than secondary. But once you have, there is an aryl group, now this aryl group can stabilize the charge through the charge delocalization into the phenyl ring. That means the stability here in this case with styrene, its secondary is more stable than the primary, and that makes it the branched is more preferred than linear. Is it clear? Do you have any question? If you have any question, let me know.
No, sir.
Okay, thank you very much. So this is where the branched becomes more favored, and then all of a sudden you see the branch product forming is much more than the linear. Okay, still as you can see, you cannot prevent the other product formation completely. Okay, 88:12, but sometimes it is good enough. See, these reactions are very simple and effective. So even if you have this sort of side product formation, this is a golden reaction anyway, right? To create some sort of this stereogenic center by other method and cheaper method is going to be difficult, right? And your starting materials are easy. All the charge starting materials are easy. Catalyst is well defined and everything put together. Even if this is a problem, 88:12, it's not exclusive, but good enough to do this reaction. And then only thing that left is if you have a chiral ligand for rhodium, it's a bidentate ligand usually. You have seen in the last class, some of these last two classes, this chiral ligand will give the enough opportunity to generate this stereocenter in an effective manner. Okay. Well, I would not, because we have the time restriction overall in these courses also. So I'll stop over here for the hydroformylation reaction. These are fascinating topic. You can read about many asymmetric reaction that is done. Many pharmaceuticals like real drug molecule, real medicines are prepared by utilizing this sort of simple technique. Okay, I'm not going to give you way too many examples here or any examples for this particular case, but there are plenty. I mean, you will be, naproxen, for example, is one. There are many drug molecules that can be prepared by these methods, and these are truly effective method out there. Many compound which has acid group, like all the profen series, ketoprofen, ibuprofen, like these are common medicine, right? Ketoprofen, ibuprofen, and all the profen series, there are like 10 of them profen, right? Profen series of medicine drug which are readily available in the market. You can go ask any pharmacy, they will give you this drug for different reason, or the doctor will suggest these drugs for different reason. All these can be prepared by utilizing this simple technique. And you can imagine if a ibuprofen tablet is so cheap, that inherently means that the reaction that is synthesizing this ibuprofen has to be effective and has to be utilized in 100 kg scale at least, because these are worldwide supply, right, of this molecule. Anyway, so moving on, we'll bring to another topic, which is again I have touched upon briefly. I will touch upon again here. This is the Monsanto acetic acid process. This is your one of the again very exciting topic. And as you see over here, you start with methanol, start with CO, you get acetic acid. This is how the world supply of acetic acid, like vinegar, right? You imagine how much vinegar we are using for just cooking purpose. Forget about other usage. So these vinegar or acetic acid can be prepared very easily by this rhodium or different iridium catalyst in presence of hydroiodic acid. What is happening here? So methanol is converted to methyl iodide in presence of HI, and then this rhodium biscarbonyl iodide adds into this methyl iodide to give this 16 electron to 18 electron species. It's an oxidative addition into the methyl iodide bond, so the metal inserts over there. Essentially, so it could be an SN2 type of mechanism, like organic SN2 type of reaction mechanism it could be, and then it's a alpha migratory insertion, so the methyl group transfers, as we have discussed briefly in quite a few cases. We can show that alkyl transfer is happening into the CO, not the other way around. CO is not migrating into the metal alkyl bond anyway. So alpha migratory insertion gives you a 18 electron to 16 electron complex. And then, of course, you are doing this reaction under pressure of carbon monoxide. So you see that carbon monoxide is incorporated into these reactions to give you these 18 electron species. From there, reductive elimination gives you the iodide over here, and this COMe reductively eliminate to give you the acyl iodide, which then hydrolyzes to give you the acetic acid. Okay, once again, very briefly, what you have over here is the 16 electron complex goes to 18 electron, goes back to 16 electron, goes back up in 18 electron, goes back down to 16 electron again, right? Oxidative addition here, and CO migratory insertion there, and then reductive elimination gives you the MECOI, which hydrolyzes to give you the acetic acid compound, which is fair enough, which is simple enough. And overall, these reactions is first ordered with respect to rhodium, first order with respect to methyl iodide, which is telling that this step is the rate determining step. Oxidative addition of methyl iodide is rate determining step for this reaction. This is simple process. It occurs, and these are done in presence of HI. Why HI is required? Because in the methanol to methyl iodide step you need HI, and methanol and CO are the main component, and the hydrolysis happens at the end. It's a high pressure reaction, high temperature reaction for sure, but this works pretty easily. So next, we are moving little bit faster here because we have quite a few things to discuss today and also in the next class. I hope this Monsanto acetic acid process is clear. Any question on the Monsanto acetic acid process?
No, sir.
Okay, thank you. So traditionally it started with historically it started with rhodium, but for nowadays for industrial process it can be iridium. Mechanism remains similar, but rhodium and iridium both are used, but most often nowadays I guess iridium is used in majority of the industry, but rhodium and iridium remains two effective metal for these sort of reactions. These reactions, as you can see, at the beginning I was telling, if you understand the simple catalytic cycle or simple catalytic step, what is happening, such as oxidative addition, alpha migratory insertion, ligand association, and reductive elimination. If you understand these steps simply, and if you can count these electron, 16 electron, 18 electron, 16 electron, 18 electron, just stepwise you can set these reactions. Even if you forget the reaction mechanism, you can understand how it is going on by simply visualizing these steps. You can try to mess up the sequence of the steps, and you can see where the problem is or where the problem is going to happen. Why this has to be in this sequence: oxidative addition first, and then alpha migratory insertion, then CO addition, and then reductive elimination. Of course, reductive elimination has to be at the end because this is where the product is basically going out and forming. But other than that, this sequence, how it should be, you can debate with yourself and try to write down other mechanism and see where the problem is coming. You might will be able to solve by yourself why it would not be a productive transformation. It's not like it cannot happen. It is not going to be a productive way of product formation. Every reaction, as you know, can be microscopically reversible. So reaction, even if something can happen, it can come back to the starting material and goes to another pathway. If one pathway either leading to higher energy pathway or not leading to the product, even that reaction happens, it can again come back and give you the desired reactions. Okay. So tagging along on that pathway, what we are then trying to say is this hydrocarboxylation reaction. We are discussing these reactions sequentially because these are all interlinked. You will see once after these discussions are done, you will see there is a theme, simple theme. The reaction mechanism are almost same or similar. Okay, and that is why I think it is best if we discuss this in, let's say, in one of the classes. Okay, so for example over here you have like similar as you have seen the moment ago or in the previous class as well, that HCOCO4 comes into the picture. It loses SCO to give you HCOCO3 complex. That's the reactive intermediate. That's the true intermediate, right? And then you have this olefin that comes into picture. Olefin binds, right? So you have seen these in the hydroformylation reactions also. Hydroformylation reactions was having olefin, carbonyl, and hydrogen. Now you have an alcohol. That's all the difference it is. So the oxidative addition into the hydrogen is not into the picture anymore because hydrogen is not there in this reaction. What you have? An alcohol like methanol or ethanol. Now what will happen in place of this hydroformylation or H, this R group was previously H for hydroformylation. Now you have taken ROH, you will see an ester formation. This is another beautiful reaction, another very, very simple yet powerful reaction. You just take three really cheap reagents, right? These, I don't think anything else can be cheaper than these, right? Similar as hydroformylation reactions: olefin, carbon monoxide, alcohol. Cheapest possible reagents. These are feedstock. These are the readily available material. You can almost, no price, for free you can get. I mean, relative price saying I'm okay. So almost for free you can get this material. It is so cheap, right? So if you can produce some important molecule like this, which are expensive from this cheap material, I think that's got to be really, really interesting. Now, as I was saying, in the hydroformylation reaction, you have H over there, right, in place of OR. Now you have ROH. Anyway, the reaction starts on the same note. You have HCOCO3 formation, exactly on same note. Olefin coordinates with the carbonyl, right, as you can see over here, olefin coordinating, and the hydride is there. You can say that these are monohydride catalyst. Of course, hydride to start with, hydride is there. Right. Now here the beta migratory insertion, once again you will have an opportunity to have the primary alkyl. This is a primary alkyl, and I did not draw here a secondary alkyl, possibility of forming a primary alkyl versus secondary alkyl comes into picture, and you have then an opportunity of a primary alkyl species, as you know, will be favored. And then CO alpha migratory insertion, which is again understandable. It is done under the decent pressure of CO. So CO alpha migratory insertion happens, and then this alcohol comes into picture. Now, this is an active research area, whether alcohol, how alcohol really reacts, whether alcohol, whether alcohol really directly attack in here or alcohol binds over there and then attack. Well, this debate is still ongoing, or some proof is there what we have drawn in here, but again this can be the detailed simple mechanism what is exactly happening where ROH adds there and then migrates. Of course, a lot of computational studies, a lot of experimental studies are done. Let's not get into too much of the details, but what we see is overall this regeneration of HCOCO3 from these to give you the ester product. of course, as I was also mentioning, you can have the possibility of a branch product. This is the linear product. The branch product you could imagine would be the COOR, right? Let's say RCH3 COOR. This branch product is also possible. In those cases, you can again imagine that a stereogenic center can be generated or an asymmetric center can be generated, which will be fascinating, right? Which will be truly exciting for these sort of reactions. Okay, so we will be brief here. So this is the hydrocarboxylation reaction. Okay, one thing to add is the dilemma of this step, right, which we did not discuss too much, maybe not required for this course, that whether ROH adds in here directly or ROH adds to cobalt first, and then that addition is happening, right? So this sort of intermediate can be calculated. This sort of intermediate can be calculated by DFT studies, and experimentally we can try to see what may be happening, but overall it would lead to this hydrido cobalt carbonyl species formation. Okay. All right. Any question on this in particular?
No, sir.
Okay, thank you very much. So what we have seen, just to briefly recapitulate, what we have seen, that a Monsanto acetic acid process, which is very simple and little bit different than compared to what we were discussing before, an oxidative addition into the methyl iodide, and then alpha migratory insertion and reductive elimination gives product. But before that, that linear branch product formation, how linear products are controlled or formed in a much better shape by introducing a phosphine ligand. But then again, linear product sometimes is not that exciting. It's the branch product that is even much more exciting. We come back to the branch product formation with the formation of styrene, or by taking styrene, the phenyl ring stabilizes it and so on. And then we have seen the Monsanto acetic acid process. All of these hydrocarboxylation again is a truly exciting reactions. Okay, it is really again done in a very large scale wherever it is required. Now the next, a very related and I would say perhaps much more exciting industrially as well, okay, and that is the hydrocyanation reactions. Okay, these processes are similar. These are no different processes than hydroformylation or hydrocarboxylation. These hydroformylation, for example, linear versus branched is the same problem. You have to solve it. Hydrocarboxylation, linear versus branched, you have to solve it. And then the reaction mechanism are similar. Of course, reagents are a little bit different. In all these cases, you are having an olefin as a common material. Here also you have olefin, right, as the common starting material. Here you don't have hydrogen or CO, but you have HCN. Of course, as you know, HCN is a poisonous gas, very, very poisonous one, right? But in industry, if it is used really properly, with proper precautions, HCN is dealt with pretty efficiently in industry. It works quite well. Well, see, this is when the handling of this material becomes tricky. In academic lab, it is difficult because the proper precaution and students working are a concern. But for industrial process, these are not an issue. These can be done very easily. Okay, so these processes are happening quite effectively, and you see the cyanation reactions occurring quite efficiently in there. Now you have the opportunity to make it as a branch product and linear product. How? exactly same mechanism or similar, not the same mechanism, similar mechanism. So you have in this case nickel. Previously mostly you have seen rhodium or iridium catalyst. Now in this purpose it's the nickel that becomes important, and for quite a number of reasons actually. Nickel, what happens with nickel oxidative addition is really facile, a lot of cases. But nickel cord, for example, it's pain in the neck to deal with. Nickel cord, you have to use it inside the glove box in synthetic setup. I'm talking, if you have the in the lab nickel cord is first of all smelly. Also nickel cord is very air sensitive. Nickel zero. And cyclooctadiene, I'm sure you are familiar with, is I have discussed also briefly cyclooctadiene. This is the cyclooctadiene, right? So cyclooctadiene, nickel cord, this nickel is very much out there, and it is very air sensitive. Two of the cord molecule is required for stabilizing this. Okay, nickel tetracarbon, nickel tetra olefin type of compound it is. Now this nickel bisphosphine molecule can add, or sorry, nickel, this bisphosphine molecule, of course you are taking a ligand, bisphosphine ligand, that is not shown over here. This is forming this nickel low valent nickel complex, not much valency is there. There is enough coordinates and coordinative unsaturation. Let me go and come back. So what you see over here is this bisphosphine ligand. Bisphosphine ligand is attached with nickel, and then olefin comes and coordinates with nickel, which is all right. Nickel cord you start with and you take ligand. This is the bisphosphine ligand you take. Now olefin coordination happens. This is pretty easy. The critical step here is hydrocyanation oxidative addition. Again, this is a deadly poisonous gas. I wouldn't recommend, if any of you are thinking of using this, use really careful, take proper precaution and proper instrumentation, as well as the safety of dealing with these things has to be taken care. HCN adds in this way, and in an oxidative addition or oxidative addition manner. Now the true question is whether you are going to get a hydride transfer over here or hydride will transfer there. It's the same question that we are asking all along, whether hydride transfer is going to be over here. If hydride transfer occurs over this internal carbon, you will get a primary alkyl species, right? You will get a primary alkyl species, right? So the primary alkyl species would be, as you know, this. If the hydride transfer, let's say A, mode A, so this is linear or mode A, that's what you get. But if the hydride transfer is happening at there, then you have mode B, right? You have mode B, that is the branch product formation, right? You have mode B, that is the branch product formation. As you know, if this R is alkyl group, alkyl like aliphatic alkyl group, then you are going to get the linear product formation, the linear, if the R is alkyl. If the R is not alkyl, such as benzyl or phenyl, sorry, phenyl or aryl group, naphthyl, phenyl, these will prefer the branch product, which is drawn over here. Once again, I repeat, let me go back and come back again. So if the hydride transfer happens over here, that's the linear or the primary alkyl intermediate formation. This would lead to the linear alkyl cyanide. Linear alkyl cyanide, right? This is what you would get, linear cyanide. Of course, this is an important reactions, right? This can be controlled, as you can imagine, by the phosphine ligand or other ligand that is out there. But if this R group, the linear product is the major product when R equals alkyl. if you have an alkyl group, simple alkyl, aliphatic substituent, you get the linear product. But I would say this one is even more important. As I said, that this center is the stereo center generation, stereo induction is happening, and this phosphine ligand can block one side, like which side of the attack it is happening. It can control that, or it can control basically this hydride transfer intermediate, how it is happening, and then that will dictate whether you get a linear product or a branch product, and or the stereo center can be generated properly, right? This cyano group which is sitting over there, which is very ideally sitting, then can undergo reductive elimination to between this carbon and CN to give you the branch product. Either you can get linear product or branch product depending on the situation. If it is R equals alkyl group, you get the linear product. If R equals this phenyl group, you get the branch product that is shown over here previously as I was showing, right? Now this branch product is stable because if you have a phenyl ring over here, as I was telling you earlier also, it could delocalize, the charge could delocalize. This charge delocalization would be quite exciting if you have the alkyl group is over there, right? We have seen it before, but in this case, of course, you have an opportunity to create a stereogenic center as well by taking a chiral ligand. If you take a chiral ligand, once again, this will give you an opportunity. This is the chiral ligand. This will give an opportunity to do this reaction in an asymmetric fashion. Okay, so this is the final slide of today. What we are seeing is the importance of the hydrocyanation reaction. Well, hydrocyanation reactions industrially used a lot, a lot. For example, this is a butadiene. Okay, butadiene, of course, an aliphatic molecule, alkene molecule, conjugated olefin molecule. You take, in this case, you don't have to take any other ligand other than nickel cord, right? So you take this olefin and this nickel cord and HCN. It's tiny bit of nickel cord. It's expensive. Nickel cord is expensive, right? Well, if you are preparing in industrial scale, it's not, but then this is a sensitive reaction in any way. What you do is you do the double cyanation reaction. Okay, you do the cyanation on this olefin as well as that olefin. Let me go back and come back. So you have two olefin here, one olefin here, another olefin here. You do the hydride addition here and cyanide addition here, HCN addition across the double bond. Similarly, you add hydride here, cyano here, HCN addition across the double bond. So it's a dihydrocyanation reaction, right, on the olefin. Okay, fantastic, big deal, and quite exciting because this is how you see you have increased the number of carbon by 2 on the butadiene, right? So it becomes nitrile, right? Adiponitrile. This adiponitrile is a really important intermediate to make these corresponding amine. If you reduce this nitrile, you get diamine. Okay, if you make this diamine, then you can react with this adipic acid, which is again, these are, of course, all of these are relatively cheap material. You get nylon 6,6. Of course, nylon can be of different type. This is one type of nylon you get pretty easily. See, this is fascinating because I would say these are important and simple reactions. It works quite effectively and it works in industrial scale. A lot of these nylons are prepared by these methods. And you know the usage of nylon and how much nylon is required. And butadiene is readily available, relatively readily available. These are reasonable reagent. You get adiponitrile and adipic acid and the corresponding amine. You condense it, amine as well as acid, you get an amide unit. So overall, what you have in nylon here is this amide bond, right? Amide bond. You cleave amide into amine and acid. It's the same thing. I mean, of course, this acid you can generate from there as well. CH2, 1, 2, 3, 4, cyanohydrolysis. You do hydrolysis, you get this acid, right? Hydrolysis. If you do hydrolysis, you can get the corresponding adipic acid, which is again quite important and simple. You have butadiene, adiponitrile, adipic acid, pretty much from the same starting material. So you have taken just the butadiene, you have done the hydrocyanation reaction, double hydrocyanation reaction. You get both the adipic acid upon hydrolysis and upon reduction at the corresponding amine, and then you just condense it. You get nylon. I think this is very effective reaction, right? Don't you agree that these are truly industrially marvelous reaction, right? These are the ones which would make sure that this sort of catalysis has true values, and these can serve human race in many different ways. Of course, we have nowadays problem of plastic, nylon, and things, but you imagine the bad effect it has, of course, the good effect or the industrial value it has, of course, and on many other reactions that you have seen, the value of the homogeneous catalysis is immeasurable. Okay, I think I'll stop here today. We have, I believe, 2 more classes left. Some more exciting topic we'll discuss. If you have any question, we'll discuss right over here, right now.
Sir, as in previous slide, we were talking about the phenyl naphthalene. It means rings are increasing.
Yeah.
So, because of that, branch will prefer, or if we will see the anthracene also, so same thing will goes.
Yeah, well, branch you will get for both in all the cases, phenyl, naphthyl, and anthracene. All the cases you will have the branch product formation. Okay,
Oh.
phenyl, naphthyl, anthracene, all the cases. It's the same logic that these will stabilize the alkyl. But of course, as you keep on increasing the ring size, that will also have another effect of steric effect, or it's not like linear effect you will be able to add up all the time, but all of them will give you the branch product, branch product as the major product. Now, what are the other substituent you have on the phenyl as well as on naphthyl as well as on anthracene? That will dictate the product distribution. Previously, as you have seen, linear is to branched. When the linear product is major, could be 4:1 or 9:1, depending on the ligand, depending on the condition. Similarly, depending on the condition, branched into is to linear for these sort of aromatic cases will also vary. Okay. Yeah. Any other question that you may have? I think these are very, very effective, simple, effective, and it makes sense that why these reactions are so used. And these are age-old reactions. These are not new reactions, but still people are working a lot on these to improve things. Because what happens in, in any synthetic reactions, let's say a reaction is good with a given set of condition for a given set of substrates. But the moment you change any component of it, things are difficult and different. Sometimes reaction mechanism itself changes. That means that you have to re-optimize everything. You have to check the catalyst, with which catalyst to use, which metal to use, which ligand to use, what temperature to change, what pressure to vary, every parameter that you can imagine. The moment your constituents or the substituents on an organic molecule changes little bit, even let's say phenyl versus naphthyl, it's not that the best method for phenyl will be the best method for naphthyl as well. If you want to do an industrial reaction, let's say 100 kg scale reaction or 1000 kg scale reaction with phenyl, the same method may or may not be applicable for naphthyl. You have to redo everything. Sometimes you have to change the catalyst itself. Catalyst, ligand, solvent, temperature, pressure, every parameter you can think of. You have to re-optimize. You have to rediscover the catalytic cycle in a way. Okay. Of course, this, whatever is giving phenyl product, naphthyl product will be formed, but if it's not like product will not be formed. I'm not talking about that, but is it the best reaction condition out there for phenyl as well as naphthyl? The chances are not really. The best reaction for phenyl is not really the best reaction for naphthyl. Okay, for naphthyl you have to redo all the experimentation, right? This makes things really complicated at points, but in industry it's not like academic lab. Once you have a set reaction, you want to make this reaction go again and again, let's say for considerable amount of time, let's say years after years you would like to go. So that's fine. But in academic lab, what happens, we are trying to figure out many different things. So yeah, the demands are different. You have to, in the industry, you may have to prepare one molecule again and again and again for the next 10 years. Of course, you have to do a lot of R&D to do many other development, but for that particular reaction, once you have developed it, you have set your engineering skills and all the engineering protocol as well as the chemistry protocol, all the safety protocol and everything. Once you set it, you don't want to change it way too often. So that's why at the beginning, when the development is going on, it's better to have many input at that point. It makes much more sense. But once it is fully grown up or fully developed method, if anybody wants to make a change, it becomes difficult because already a lot of effort has gone into both financial, resource wise, and all sorts of things has been done. So changing things become difficult. Okay. Yeah. Any other question you have?
No, sir.
Okay, so we'll stop it here today. Okay, and as you said, tomorrow we will not be meeting, and we'll meet some other time then.
Sure.
Okay, maybe day after tomorrow then. Okay. Okay. All right. Yeah, it was nice discussing with you. Thank you very much for
Same here.
joining. Yeah. Okay, I'm stopping the recording.